Dell. I'm the Director of the Office of Highway Operations with the Federal Highway Administration in Washington, D.C. I would like to take a few moments at the beginning of this videotape to introduce the subject truck impacts on pavements and to provide a brief explanation of our objective in developing this presentation. While pavement engineers are quite familiar with the relationship between truck loading and pavement deterioration, others less directly involved in pavement design may not be. The purpose of this video is, therefore, to acquaint pavement managers with the factors that affect pavement performance, discuss how truck loadings are considered in pavement design, show some examples of the effects of increased truck size and weight, and describe how truck configuration affects pavement deterioration. We hope that the information provided will enable highway administrators and engineers to better design and manage their pavements. Although this tape only discusses truck impacts on pavements, you should keep in mind that trucks can also significantly affect bridges, highway geometrics, and safety. All of these subject areas are of concern to us and must be considered together when evaluating the total effects of trucks on the highway system. Numerous publications are available describing both pavement and non-pavement impacts of trucks. There is also a considerable amount of research currently in progress to better define truck impacts on pavements, bridges, geometrics, and safety. With this brief introduction, let's get to our discussion of truck impacts on pavements.
Transportation is the lifeline of the American economy. Improvements in transportation of people and goods create beneficial social and economic changes. The cornerstone of the transportation system in this country historically has been the highway network, which contains nearly 4 million miles of streets, roads, and highways. The interstate system is one of the largest public works projects ever undertaken and is estimated to cost $124 billion when the more than 42,500-mile system is completed. More than 97% of the system is now open to traffic. The interstate system, while representing only 1% of the highway mileage in the United States, carries 20% of the vehicle miles traveled, as well as 30% of all the truck miles of travel. The importance of the interstate to movement of manufactured goods, commodities, and other products cannot be overstated. In 1985, there were over 370 billion vehicle miles traveled on this system. On rural interstate highways, 17% of the vehicle miles of travel was by tractor semi-trailers or other combination vehicles. Combination vehicles are trucks with double or triple trailers. While the total traffic volume, as shown by the red line, is growing at a constant rate, heavy truck volume, as shown by the blue line, is growing at an even faster rate. Many of these trucks are taking advantage of the greater loadings allowed by Congress. With these increasing volumes of heavy traffic, what will it take to protect the tremendous investment that has been made in the interstate system? In this presentation, truck weights will be examined, for they are one of the most significant factors contributing to the deterioration of our highway system. The presentation will explain how truck weights are considered in pavement design and how they affect our nation's pavements. We will discuss types of pavements, effects of the environment, use of truck data in design, and effects of increased truck size and weight. 4 major elements affect the performance of pavements: the type of underlying soil called the roadbed soil, pavement structure including types of construction materials and their thicknesses, traffic loads, and the environment. Historically, pavements have been divided into 2 broad types: flexible and rigid. Flexible pavements primarily consist of an asphalt surface layer built on an aggregate base and resting on a compacted roadbed soil or on the natural soil foundation. Approximately 24,500 miles, or 58% of the interstate system, are flexible pavements. It should be noted that this information reflects the 1985 surface type and not the materials used in the original pavement construction. Rigid pavements are made of Portland cement concrete placed on a sub-base. Rigid pavements make up approximately 18,000 miles, or 42% of the interstate system now open to traffic. The essential difference between the two pavement types is the manner in which they distribute the load. The material and thickness of each layer of the flexible or asphalt pavement are designed to distribute the load over a larger area. As the load stress is passed from layer to layer down through the pavement structure, it is reduced until each layer can adequately support the applied pressure. A rigid or concrete pavement, on the other hand, functions more like a plank or a slab. Because of its rigidity, a concrete pavement tends to distribute the load over a relatively wide area and does not depend on a series of layers for load distribution. With this background on pavement types, let's discuss the remaining two elements that affect short and long-term pavement performance, that is, traffic loads and the environment. We will discuss the environment first. Some research groups and transportation industry representatives have argued that the environment is the most important factor causing pavement deterioration. Primarily, this is due to moisture, temperature, and freeze-thaw cycles that pavements are subjected to throughout their design life. These factors create internal stresses and material deterioration, thereby limiting a pavement's life. While the environment causes some pavement deterioration, a greater amount of damage is caused by heavy vehicle traffic. This finding is supported by the fact that one loop at the Asho road test conducted between 1958 and 1960 was not subjected to traffic. This concrete pavement, as shown here, is still in good structural condition today. A similar section built at the same time and subjected to interstate traffic required rehabilitation in 1975. A recent survey by the Federal Highway Administration has shown that much less pavement deterioration occurs in left lanes on multi-lane highways carrying high percentages of trucks. This finding further substantiates that it is repeated heavy vehicle loadings that are the primary cause of pavement deterioration. Basic relationships for the effects of truck weights on pavements were established at the Asho road test, which was conducted between 1958 and 1960 in Ottawa, Illinois, at a total cost of $27 million, which is well over $110 million in 1987 dollars. Trucks with known axle weights were driven on sections of road built with various types and thicknesses of construction materials. The road test established relationships among the variables of roadbed soil, load repetitions, and pavement structure. While the road test was not able to evaluate all the variables in pavement design shown here, still it is the most comprehensive test for pavement design to date. Recently, AASHTO adopted a new guide for the design of pavement structures. This new guide contains significantly improved methods for pavement design and rehabilitation. However, the basic pavement performance concept developed at the road test remains unchanged. For improved design procedures, good long-term pavement performance data are vitally needed. These data will better describe how pavements perform over long periods under a wide range of traffic and environments. In 1986, a long-term pavement performance study was initiated under the Strategic Highway Research Program. The monitoring effort includes approximately 2,500 test sites nationwide. This comprehensive study will enable highway engineers to improve design techniques and better define the relationship between truck loads and environment as they relate to pavement performance. Now let us discuss how truck weights are considered in pavement design. Many people think that pavements are designed to carry a maximum size load. This stems from the fact that both the federal government and states have established maximum legal loads for highways and bridges. The maximum load is not necessarily the critical load. In design, it is not so much the maximum size load, but the combination of both size and number of loads applied to the pavement that is important. It is both the size and number of loads that determine the rate of pavement deterioration. While it is true that a single heavy load can cause failure, this load would indeed have to be very large. pavements generally fail due to repeated applications of loads. This is called fatigue failure and can be illustrated by bending a piece of wire. The wire will endure a certain number of bends before it fails. The same can be said of pavements, namely that they absorb a certain number of bends before they fail. For the selected design period, loads to be applied to the pavement are estimated. It is important that designers have as accurate data as possible. In making this estimate, the total traffic first is projected based upon historical trends. There are many factors that affect traffic growth trends: commercial and residential development in the area, vehicle capacity of the proposed roadway improvement, as well as neighboring highways, and the overall economy of the area. Recent development of weigh-in-motion, or WIM equipment, enables better forecasting of future traffic trends. The WIM equipment allows vehicles to be weighed without leaving the mainline highway and while moving at normal operating speeds. The equipment provides gross vehicle weight accurate to about plus or minus 5%. Also, it can measure and record individual axle weights, axle spacings, and vehicle speed. The mix of traffic or types of vehicles in the traffic stream are then identified. Using historical trends and other information, the mix of traffic is forecasted over the design period. For example, if the number of 5 or more axle trucks or their axle weights have been increasing over the past few years, that trend would be used to estimate the number and load of 5 or more axle trucks that will use the facility over its design life. The number of 5 or more axle trucks is of interest because they represent the heaviest loaded vehicles and presently cause more than 90% of all the vehicle-related damage to pavements. There would be, of course, more damage if the same loads were carried on fewer axles. Once the mix of traffic has been forecasted, the designer next converts these numbers of vehicles to the number of loads that will be applied to the pavements in each axle weight class. Obviously, these loads cannot be considered individually. There are millions of loads with a wide range of weights applied to a pavement over its lifetime. Each load, regardless of size, contributes to the eventual fatigue failure of a pavement, or in other words, each load consumes a small portion of a pavement's fatigue life. Therefore, it is necessary to determine the combined effects of these loads. To do this, loads are expressed in terms of a common denominator called an equivalent single axle load, or ESAL. The AASHTO design procedure uses an 18,000-pound equivalent single axle load. This means that all loads, including single, tandem, and tridem, that is triple, axles, are expressed in terms of the number of equivalent 18,000-pound loads applied by a single axle. In the example shown, the 34,000-pound tridem axle causes 0.246 ESALs. The 30,000-pound tandem axle results in 0.658 ESALs, and the 12,000-pound single axle results in 0.189 ESALs, for a total of 1.093 ESALs for the 76,000-pound truck. Each load is converted into 18,000-pound equivalents using relationships shown in the AASHTO Guide for Design of Pavement Structures. All of these equivalents are then added to determine how many 18,000-pound applications the road will absorb over the design period. The number of applications is combined with other factors such as soil strength, properties of paving material, and drainage characteristics to determine the required design of the pavement structure. The designer utilizes these factors as inputs into established design procedures in order to arrive at the pavement thickness. The importance of accurate cumulative truck weight data in the design process cannot be overemphasized. We have discussed how vehicle weights are considered in pavement design. Now let's examine in detail how individual vehicle axle weights affect pavements. How much relative damage does an 18,000-pound axle load do? The AASHTO pavement design procedure provides for a load equivalency factor of 1.0 for this load and uses it as a base. All other single, tandem, and tridem axle loads are expressed as factors in relationship to this common denominator. Analysis of AASHTO data indicated that if a single axle load is doubled from 18,000 pounds to 36,000 pounds, the damage will increase from 1.0 to 17.12. That is to say, one pass of a single axle loaded to 36,000 pounds consumes as much of the pavement's design life as 17 passes of a single axle loaded to 18,000 pounds. Therefore, damage increases in much greater proportion than the increase in weight. The 1974 Highway Act raised the single axle maximum weight limit from 18,000 pounds to 20,000 pounds. The tandem axle weight limit from 32,000 to 34,000 pounds, and established a maximum gross weight limit of 80,000 pounds. Let's take a look at what impacts this has on the roadway. When the average single axle load increases from 18,000 pounds to 20,000 pounds, the damage increases from 1.0 to 1.57. That is to say, one pass of a single axle loaded to 20,000 pounds consumes over 50% more of the pavement life than one pass of a single axle loaded to 18,000 pounds. This means that a pavement designed to absorb 10 million applications of an 18,000-pound equivalent single axle load over a 20-year period would wear out in 15.3 years with the application of 10 million 20,000-pound axle loads. If you take into account that the same amount of goods could be moved in fewer trucks with 20,000-pound axle loads, the increased axle loads would cause the pavement to wear out in 16.4 years. Let's look at tandem axles. This figure compares the damage of a truck fully loaded to the 1956 legal limit of 32,000 pounds per tandem axle, a truck fully loaded to the 1974 legal limit of 34,000 pounds per tandem axle, and a truck overloaded to the illegal weight of 40,000 pounds per tandem axle. There are significant increases in damage with small increases in axle load. Also note that most of our highways were built to the 1956 limit, and weight increases of 1974 are contributing to their accelerated deterioration. The Surface Transportation Assistance Act of 1982 also had an effect on pavements by increasing the allowable length and width of truck trailers. The increased trailer volume allows more cargo to be hauled, and thus heavier axle loads to be applied to the pavements. It is these heavier axle loads, as well as number of loads, that are of concern to pavement engineers. Several bills have been introduced in Congress over the last few years that would result in an increase in average truck axle weight. One such proposal calls for removing the vehicle maximum weight limit of 80,000 pounds and letting legal axle weight limits control. Let's look at the effects of removing the maximum weight limit. First, there will be increased use of a new generation of trucks. The 1982 Surface Transportation Assistance Act allows tractors with two 28-foot trailers, called Western doubles, to operate on all interstate highways and some primary highways. Longer combination vehicles, or LCVs, which can now operate in certain states, will be used more frequently if the weight cap is removed. These LCVs include the Rocky Mountain Double, the Turnpike Double, and the Triple shown here. One way to illustrate the damage done by the various truck configurations is to determine the number of 18,000-pound equivalent single-axle loads, or ESALs, each truck type applies to the pavement to carry 1,000 tons of cargo. Of course, this will require several trips by each type of truck. It is assumed that the gross weight cap of 80,000 pounds has been removed, and trucks are loaded to their highest practical operating weight. The use of Western doubles with their single axles applies the most number of ESALs, that is, 175 for each 1,000 tons of goods moved. The use of triples applies 163 ESALs. The use of Rocky Mountain doubles applies 144 ESALs. the use of conventional tractor semi-trailers applies 134 ESALs, while using turnpike doubles applies 80 ESALs. In other words, different truck configurations cause varying levels of pavement damage while carrying the same amount of cargo. The importance of accurate truck weight data in pavement design has been discussed. Also, the large impact of increased truck size and weight has been illustrated. From this discussion, it is apparent that the strict enforcement of the congressionally mandated weight limits on the interstate system is essential in order to preserve the pavements. The important point to remember is that even if all other factors remain the same, as axle weight increases, the amount of pavement damage also increases, and the expected pavement life decreases. This resultant pavement deterioration substantially increases the need for additional rehabilitation funds. Realizing the potential damage to the nation's highway system caused by increased axle weights, former Federal Highway Administrator Frank Turner has proposed a new generation of truck that would cause less pavement damage by controlling axle weight while allowing heavier gross loads. Under the Turner proposal, the single axle maximum load would be reduced from 20,000 pounds to 14,000 pounds, and the tandem axle limit would be reduced from 34,000 pounds to 24,000 pounds. The vehicle gross weight would, however, be allowed to increase from 80,000 pounds to 105,000 pounds. The number of ESALs applied to the pavement to move 1,000 tons of cargo would be reduced to 40. This is more than 3 times fewer ESALs than for the conventional tractor semi-trailer to move the same amount of goods. By the way, the Transportation Research Board conducted a preliminary study of this proposal. This study estimates that allowing truckers to exceed the 80,000-pound gross weight limit while reducing axle loads as indicated in the Turner proposal would result in $250 million reduced pavement damage annually. At the same time, it would result in substantial economic benefits to truckers. A more detailed study of this concept is underway. This presentation only discusses how truck size and weight are considered in pavement design. There are several other factors that must also be considered when comparing truck configurations, including economic trade-offs, safety, operational considerations, and the effects on bridges. The challenge of the future is to reach an equitable balance between reducing the cost of transporting goods and providing safe and cost-effective highways. Transportation costs have been reduced, and this nation's economy has benefited greatly from the improved operating speeds and from increases in the weight limits on the interstate system. Our future policy position on proposed changes to the existing size and weight limits must be based on a careful analysis of the nationwide costs and benefits of the proposed changes, while maintaining responsible stewardship over our highway system.